So I'm going to talk mostly about what we're working right now with your own Ilya and Evgeny, and also with my PhD supervisor, Nick Stone, who is currently at the Hebrew University, but is moving to somewhere in the United States. Okay. And I'm going to talk about mostly the AGN channel and the hierarchical growth problem. So let's start with some motivation. I think this is a figure very well known to many of you, and many of you contributed to some of that. And this is all our observations until 03 for black hole, and neutron star mergers. And since 2016, we've seen all those black hole mergers, and it raised a lot of questions. We started this golden black hole dynamics research era. One of those questions is, how do binaries form that they can actually merge? Because if you take a binary star system and try to merge them, the time it would take without any interference is longer than the AGN lifetime. So that's one question. Another question, we see many black holes in mass ranges above around 50 solar masses. And as you can see in this figure by Sper and Mapelli, which is the x-axis is the zero main sequence star mass, and the y-axis is the remnant mass. We have this gap of formation of mass of these black holes in formation due to parent stability supernovae, which just explode stars without leaving any cores. So we have this gap, and yet we see many black holes with those masses. So that's another question. And like I said, it's a golden era, so many people had very good ideas on how these black holes are forming. So we have like first generation mergers, we have some dynamical and some isolated systems. Some dynamical, so clusters and triples bring black holes closer together to eventually merge. Some isolated systems, people believe that if two stars have like a common envelope, then everything is mixed and creates this opportunity to merge faster. But also the question, one of the answers for the mass gap is say, okay, maybe we have black holes that merge several generations, which raises even more questions. So there are some suggestions from globular cluster how it is possible, or from triples. And one of the channels to answer all of those questions, and it fits both the isolated binary and the dynamical properties and the hierarchical mergers, is the AGN channel. It's like one to fit them all. And I'm Manik, my supervisor was a really strong advocate while he was doing his postdoc, and still is. And I'm continuing his legacy in that sense. So to understand a bit what am I talking about, let's understand what do we know about AGN, or what are AGN. So the idea of AGN is because we see many galaxies with centers much brighter than the total luminosity of the whole galaxy. And it raised the question, how do we get such energies? And the main consensus today is we have this accretion disk, which is in the middle here, around the supermassive black hole. And that's the almost most efficient way to create luminosity. So that's how we get it. And we get all the different properties from observation from these accretion disks. But there are two problems. One, the model for accretion disk is based on mainly 73 paper, okay, that is very good for stellar mass object accretion disks, but it doesn't scale up. There are many problems. And the second problem today, that theorists and observers went their separate ways in AGN specifically. So a lot of theorists still use this model to fit what we observe. But also theorists ignore completely what we see. So we see a lot of variability. We see very weird lines and weird spectrums that cannot be explained by this or actually almost any model today. So AGN is kind of a mystery that we still need to solve, and I think understanding how black hole populations fit into that picture will help us might solve some of those mysteries as well. So like I mentioned, the basic model is the Shakura-Svinyaev model. It's a very good model for stereo mass systems. It fits almost perfectly. It's a really good model, but it has several problems, and one of which is the outer regions of the disk are unstable to gravitational perturbations, which means like that means that stars would form in the disk. If stars are forming in the disk, according to Thomson and Serco and Goodman, then there are stellar winds and supernovae, and the disk will heat up also. So there is like a slightly different model. The problem with this is that stars will stop forming eventually, and the disk will become unstable again. So what we suggested with my supervisor a couple of years ago is that you put black holes in the disk. Black holes heat up the disk much more efficiently, and we found like some kind of model which fits these black holes in the disk. So there are good reasons why would there be a lot of black holes in the disk. More than that, so we kind of assume that the black holes are formed from this strong star formation in the beginning, but it doesn't have to be so. So one of the plots in our paper is showing estimation of, it's a bit cut off here, but it's almost approximation of the number of black holes at each radius. And the shaded region, which is I want you to focus on, is the number of black holes that can align over time from a nuclear cluster. So you have a nuclear cluster mass function for the black holes. So you don't have to even form in the disk. You can, like, black holes can get to the disk very easily in several ways. And yes, the axes are cut off, sorry. So the x-axis is the distance from the center of the supermassive black hole, and the y-axis is the approximate number at each radius of black holes. And this is like a 2D to 3D map, like 3D to 2D mapping of the spherical distribution, and this includes the time it takes to realign with the disk. So the shaded region is the potential number of black holes in the disk only from realignment from a nuclear cluster, so they don't have to even form in the disk. So we have all these black holes in the disk. What do we do with them? One of very good calculations, but again for protoplanetary disks, so everything with the caveat that these initial calculations are done for protoplanetary disks, is calculating the interaction of a single perturber with the gas around it. And several papers, this is a type 1 torque, but we'll also in our paper with Evgeny, we include thermal torques that we'll show in a second, showed that there is some net torque exchange between the perturber and the gas, which causes migration, radial migration. This is from gravitational interactions. And there is another expression from thermal interactions. So if the object in the perturber is hotter than the environment or colder than the environment, there will be some thermal perturbations. So a small black hole would accrete some mass and would create a really hot zone. So that's how it is explained in the black hole sense. With planetary, you have these gas giants that may be hotter than the protoplanetary disks. So we include both of those, and in our recent paper that Evgeny led, we calculated the torques for given specific black holes and specific disks. And what you notice here is that you have this dashed line and solid lines. So the difference between the dashed lines and the solid lines is the actual torque sign. So the dashed lines are negative torques, which means everything is migrating inwards, inside. And the solid lines are positive torque, which makes everything migrate outwards, which effectively creates this region where objects migrate toward this region for both sides. And effectively, this is called a migration trap. So Yevgeny made this really nice plot in his paper, which basically creates a migration trap region. So the blue line, so the x-axis is mass, and the y-axis is R in RG units. And the blue line is basically the RG where migration trap is happening. The red line is also very interesting. It's basically an anti-trap. So you can see by the arrows, it's very intuitive, the direction of the migration. The anti-trap, which means that, so even if your black hole starts here, it will migrate towards the trap, which is very important for later. By the way, if you have any questions, feel free to interrupt in the middle. So in Israel, it's that's the way it's done. Huh? It's the norm, yes. Okay. So we did this background on AGN. One more thing about the mergers, which is important, that when two black holes, so one of the problems for hierarchical mergers that I mentioned here, you see hierarchical mergers, is that most of black holes have some kind of spin, even if it's small. And the direction of the spin, if it's a triple system or a cluster, will be random. If it's AGN, it might not be random, but it's not the world is not absolutely aligned to the zeroth order. There is some asymmetries in the orbit. So, and when there is asymmetry in the orbit, at the end of the orbit, depending on the phase and the directions of the spins and the strength of the spins, the gravitational wave will be not symmetrical in all directions, which causes, and due to momentum conservation, this will generate a kick for the product of the merger. And sometimes very strong kicks, like the range depends on the spins and the mass ratio. It goes between tens of kilometers per second to thousands of kilometers per second. So, if you know your systems, then most of the clusters, if you're 1,000 kilometers per second, you escape the cluster. Unless you're really, really close to the center, you escape a lot of systems, most systems with those velocities, which creates a problem for hierarchical mergers. So how do you create a system where you have a merger and it doesn't escape the region where there are many black holes? So this is the first thing we're investigating. Luckily, all the orbital parameters can be expressed without dependence on mass, on scale. So it's all in units of RG and C. So velocities, you actually have absolute numbers, and radii in units of RG. So this is just to show that we can do it. So let's start with describing our system. Okay, so we assume some kind of AGN or a rotating system around a supermassive black hole. There is a binary at some RG. And right now, with random spin, more realistically, the spin will be more aligned. So the effect would be even less strong. So what you will see, the result will be even more robust when we include a limit for the direction of the spin and the size of the spin. But right now, we're randomizing both the direction and the magnitude of the spin for specific mass ratios. So we don't randomize the mass ratios. And we choose, for each RG, we randomize 10 to the 4 mergers. So the difference between each run is not the spin magnitude and the direction, but also, even if I choose a specific spin magnitude and direction, unless they're aligned, there will be some distribution of kicks because of the mergers at different phases will make different size of kicks, and different sizes and different directions of kicks, which is important because we're comparing to the orbital velocity eventually, to the large orbital velocity.
Sure. Yes. What do you mean by the large orbital angular momentums are aligned? Is that the...
So the orbital momentum of a binary compared to the supermassive black hole is aligned with the binary orbital momentum. Okay. So we calculate all the orbital parameters using these equations and adding the velocities and calculating all the orbital parameters. And we calculate the distributions for each R specifically. So it's not a 2D distribution. It's a distribution for each R, but it's all normalized to a single scale. So you'll have a better idea what you see. So let's start. Let's start with the eccentricity, because I think it shows the best what happens. So this is two different mass ratios. I'll mostly talk about this panel, because this is the strongest effect, the equal mass ratio, and we'll see what's going on. So the y units is Rg, the x units is Rg. The y units is the distribution for eccentricity for each radius. Okay, so it's PDF for each radius. The yellowmost color is 1, the blue is 0. So we see some increase in distribution with R, basically, and there's like some distribution here. As soon as we reach E equals 1, basically everything above here, I consider that it's ejected from the system. So you move to a hyperbolic orbit, and you're ejected from the system. So we see that in the outer regions of any disk, you are ejected from the system, but unless you're a small supermassive black hole, this is so 10 to the 6, 10 to the 7 Rg is like very unrealistically that the disks span until these scales, but this is just a test. So the major bulk of the parameter space, the black hole product of the merger stays in the system. And I think any other dynamical approach to black hole mergers cannot say this with these statistics. So there are ways for a product to stay in the system in clusters, but not in these numbers, not in these statistics. We do get very high eccentricities at some regions, but at the closest to the black hole, even the eccentricity is pretty small. So we don't even, the changes to the orbit are minimal. And like I mentioned before, these statistics are taking into account random spin directions for the single black holes. Realistically, in an AGN, everything will be aligned with the gas and with the orbit. So the distribution would be less great. So the asymmetry would be smaller generally. So this result is even more like the worst case scenario. So the result is very robust in that sense. Yes.
Can I ask a question? So about the plot on the right.
Mm-hmm.
I was curious why there isn't any behavior with eccentricities of 0.7 or something, right? Meaning that you seem to hit a wall at roughly 10 to the 5 or a bit over 10 to the 5 gravitational radii, where above that everything just immediately goes to being unbound.
No, you have this distribution like that. It's a large distribution. So the distribution is like for each radius, so it's a vertical, right? So you have a large parameter space in this radius. Okay.
You're right. I said this badly. Sorry. Yes, there are things with eccentricity of 0.7. I see that. I mean, why there's sort of nothing with larger. So there is a vertical wall. Why do you don't have sort of an extension of this curve to let's say separations of 10 to the 6, right? At those points, everything's unbound. Whereas I would have expected that 10 to the 6 corresponds to what 300 kilometers per second Keplerian velocities. So you're saying that there's basically you don't have any kicks that are less than a few hundred kilometers per second. Is that right? I would have thought there would still be some because of
there. Okay, so it's a matter of the density of the color scale basically. So I'm thinking if I would put this color scale in log space, then you would see some events like here as well, but it's very small numbers. We have 10 to the 4 numbers, so if you have 10 events or like few tens, you will not see it in the plot. Yeah, so maybe maybe the takeaway from this is do like 10 to the 6 events and do different scaling to see what's going on in the smaller. Yeah, but there are definitely events where the kicks are weak.
Can you say again what the distribution of spin magnitudes was on the initial?
Between 0 and 1. So
uniform.
Yeah. So this is the worst case scenario, basically. It's probably so what we plan to do by Iliad's suggestion, we're going to limit the spin to 2 or 3 cases, like 0.1, 0.7, or something like that, just to have a feel. But this is the worst case scenario, and because it's uniform, and I think that any change we make to the distribution will make even more events not escape. so yeah. But yeah, so we're going to change that. It's in preparation still. Yeah. Questions? Any other questions? Okay. So let's talk about inclination. This is also very interesting. So the red and white lines are approximately scale heights, of a disk with 10 to the 6 and 10 to the 9 solar masses. Just to compare the inclination to the disk, because it's not enough for inclination to be more than 0 to escape the disk. You have to be more than the scale, escape the scale height, basically, of the disk to be outside the disk. So we see that even in the low region, in the smaller radii, we have many cases where the merger actually escapes not the system, but the disk, outside the plane of the disk, and the orbit becomes very inclined. So the question is, what happens to those black holes that escape the plane of the disk? And another question arose is that, okay, so if you have very eccentric orbits and you escape the plane of the disk, maybe, so we ask ourselves, maybe the pericenter is also changing somehow from if the kick is strong enough. But unfortunately, as you can see, you either escape the disk, which is represented by this distribution here, or you basically stay in the same orbit, in the same and with the same energy. You don't the energy isn't changed too much, which is not surprising, but important to check. Okay. So this is slightly different version of the same plot I showed you before, slightly less nice, because there are slight difference in some of the assumptions. So the disk solutions here use more realistic opacity. So there are some jump solutions. And also, in our previous paper about migration traps, we didn't take into account some small correction that I do take into account in this case. We do mention it in the paper, but we don't show it in the main plot. And so it's slightly different. So all the red dots are basically the outside migration traps it's the same RG as a function of mass. We can see that in some cases we have several migration traps. And the cyan dots are the empty traps that I mentioned before. The X's, so I mentioned before that we want to see what's going on with the eccentricities of when the orbits, with the orbits that escape the plane of the disk, and and we decided to look at the statistics at migration traps because there we would assume black holes would accumulate and possibly will have hierarchical merger and higher chances for mergers in general. So what we want to take a closer look what happens in specifically migration traps. And so we took the results for general statistics because it's scaleless and applied it to the specific location where the X is. So in places where we have several migration traps, we take the outside, like the further outside migration traps. But because it's a small region, doesn't really matter what's that. And we show like this line to show the limit of the migration trap region. But at the migration traps, we calculate the realignment time distribution. So you escape the plane of the disk. How long will it take you to realign with the disk? At the migration traps, and generally, not too long. So until now, so most of the mergers in a disk would stay in the system without even interacting with the gas, just in like AGN, like a supermassive black hole system, most of the mergers will stay in the system. And if you escape the disk, you will come back pretty fast. So we're talking about the majority of cases at most, like at lower masses, it will be around a few tens of thousands of years. At the higher masses, okay, so maybe 1 million years to realign. But the time scales of AGN lifetimes are somewhere between 10 million and 100 million years. So this is much shorter than an AGN lifetime. So you have enough time to get merged, escape the plane, and go back to the same place, back to the trap, basically where there are many black holes. So then you can merge again and again and again. Just so it will be easier to read this plot, because this is quite confusing. So the distributions here are vertical, but they're not at the same radius. So there's like, you need to map. So for example, for 10 to the 7 black hole, you need to map it to around 10 to the 4 RG. Okay? For 10 to the 8, you need to map it around 10 to the 2 RG. So like it is important to map it. It's not the same, but it's not the same RG. So this is just a way to get a better understanding on the time scales. Okay. So the first one is for a mass ratio of 1. So like the strongest kicks. Obviously, if we take a smaller mass ratio, the time scales will be much shorter, as expected. So it's just as shown, but so basically all the time scales are shorter than this distributions. This is like again the worst case scenario of mergers. Okay, so pretty good, robust results until now. But the question is, so there are several questions. First, what are the actual physics of the migration traps? It's problematic. And second, if you consider that the migration traps are correct, and you have to take into account the interaction of gas and perturber that's similar to planetesimal, there is another type of interaction, which is called the type 2 torque, where if the perturber is really massive, then it opens a gap, basically, in the density. So the way some review told it, and Evgeny described it later today, actually, then the gravitational torques are stronger than the viscous torques. So it pushes away the gas faster than it can refill the gap, basically. And a gap opens, and if a gap opens, then the calculations for the migration traps are not correct. And I have no thing. So we wanted to see like how heavy do you need to be to open a gap in the space where we plotted the migration traps. So just for intuition, this is the migration traps, and the red line is also the anti-traps. So for intuition, so let's look at it a bit bigger. So there is a simple criterion to calculate the mass you need to open a gap in a disk, depending on the mass and on the surface density of or some parameters of the disk. And so we did that, and you have some contours here that show you the color scale is the actual mass. So the black line here is 10 solar masses. 10 solar masses, I don't know if many of you know, but if you take that first plot of the remnant mass and the stellar mass, and do some zero mass function and calculate the remnant mass function, then 10 solar masses black hole is around the mean black hole, so 10, 11 solar masses. So basically, for the smallest black holes, and even smaller, we have even smaller supermassive black holes, migration traps almost don't exist for like the heavier black holes. They do exist for smaller black holes. So we would expect for smaller black holes to see mergers of smaller black holes, basically, smaller stellar mass black holes. So if I'm 10 solar masses, I can basically ignore the trap, migrate inwards, but here, if I meet this region, so I'm 10 solar masses, so here I'm not heavy enough anymore. Okay, the gap will close. So I do feel the type 1 and thermal torques. So here I have the urge to go back up. But here, then I open the gap again, I get the urge to get back down. And now I have an effective new type of migration trap. So we don't have an official name yet, so let's call it a type 2 migration trap for now. But this is for the smallest black holes. What happens in the bigger black holes? In the bigger black holes, you have mergers at the traps, many mergers, until the mass is big enough to escape the trap. So we basically have, and then I go down, and I have a type 2 trap. So I basically have some kind of mass segregation with radius from the gas interaction, and will basically separate, with some limit, the lighter black holes to the heavier black holes, and will create a new region where possibly there are like a higher rate of mergers of two heavy, comparatively heavy black holes. And in observations, we already see like 60 plus 80 solar mass mergers and something like that. So we have, phenomenologically at least, shown that you can get these mergers in relative escape. So, but in some cases, if you merge enough, you will actually be able to go beyond the type 2 trap and beyond beyond the anti-trap. And once you pass the anti-trap, even if the gap closes, you will continue towards the center. So another result that we have, that we basically say, okay, so if most of your black holes originate from beyond the anti-trap, then we have a minimum mass criterion to get an EMRI in this system. Or preferably some, like you prefer masses above, statistically, above something like that. Yes?
So I see three like kind of streaks in the console.
So this is 10, if you can see, this is 10 solar masses.
Yeah.
This is 50, and this is 100.
It's horizontal streaks.
This one, the red one?
The colors.
The red one?
No, the color contours. Color map. These mountains.
Ah, like almost horizontal region.
So I assume this is associated with the opacity table.
This is what?
No,
Yes.
do you know which combination that corresponds to?
Which opacity?
Yeah, which opacity?
Let me let me think about it. Okay. So okay, so in surface density, you has like this is almost zero radius. You have initial rise, then drop, then a jump, and then drop again. So I'm guessing like this is the jump region, maybe somewhere. So if it's a jump region, maybe this is maybe it's like 10 to the 4 temperature, like somewhere around like the close to the opacity gap, maybe. But I don't. Oh, you know what? I can actually. I have the inclination plot with the h over r, and you can see the features better there. This one. Okay, so this is 10 to the 9 or 10 to the 6. So you see these jumps. This is like close to it has to be close to the. So this is the iron bumps. So I'm not sure actually what features, but I'm guessing this is what we're seeing, this jumpy region. So the iron bump, so you have, so close to the H minus region, you have like, in the opacity, you have a small iron bump, which changes the sign of the derivative, which makes these weird behaviors.
So then it might be interesting that this might strongly depend on the gas resistivity in the design.
Yes, it's definitely okay. Yeah, the location of the iron bump is definitely so the fine-tuned physics is not clear. It's not. We don't know a lot, like I mentioned in the beginning, about AGN. So this is working with the best known model right now. Of course, this will be updated with like a better model. Okay. So just as a sanity check, I want to see what would be the timescales to migrate inwards to the type 2 migration. So the timescale is the radius over the radial velocity. And we see it doesn't matter where we are, in the trap, outside the trap. The timescales are a few, like 1,000 years, 2,000 years. So if you integrate it all over that, it's still very, very short times. Unfortunately, not human lifetimes. So we wouldn't be able to see like a merger in the trap and then an EMRI of it, but very short times, which is good because that means that if you have very heavy black holes that will migrate, you will definitely see them with LISA, statistically. So it's not a rare event. You don't expect it to be a rare event. Yes. So and like Rio, right? Rio mentioned there is like a horizontal streak here, which is very close to the anti-trap as well. So we say, and generally, when you go lower, it's harder, like you need higher mass. It's not true 100%, but this is generally true. In the outer regions, the masses are so high that it's not even interesting. That's why we have a white region. But in the these masses, it's very interesting. So the question is, what is the minimum mass needed to basically pass the anti-trap without anything bothering you? So I made this plot. So this is the minimum mass in solar masses needed to pass the anti-trap for different cases. And we see that generally for lower mass disks, until we have like this jump, which is corresponding to like high increasing to this jump probably, yeah. So generally it's not too crazy. So this is we see black holes with these masses. We see the mergers of black holes with these masses. So I think generally we would expect either mass growth from the gas or from mergers, and then move on and statistically have relatively a lot of EMRIs compared, yeah, as well. So I will summarize the conclusions. Black holes will stay in the system after merger. This is a very robust result and very, very good result for us. Heavier black holes can actually even escape the migration traps. And some masses that are heavy to escape migration traps but are not heavy enough to pass the anti-trap will get stuck in their new traps that are closer to the supermassive black holes, type 2 traps. And even a larger mass needed to escape the anti-trap, which will give us some lower limit on the mass expected in EMRIs, which is very nice. Some things to do in the future. So what we're already talking about is building a model for body plus disk dynamics that will give us an understanding on like how the mergers happen, like directly, and not just assume them. Comparing all the possible timescales of the model to see what can we assume like something is happening without considering other effects. And yeah, so this is generally a better AGN disk model would be needed, probably. Thank you.
how many, so you need a lot of black holes in the disk around the supermassive black hole. How many?
What do you mean you need?
I mean, you seem to. I mean, it's one of your early graphics. So
I think yes. Okay, so let's.
full of that you're.
That I believe that they're full of black holes. Yes.
It's full of black holes. So motivation. I guess I'm trying to get to the motivation for needing the black holes in the first place.
So two reasons. First is, of course, advocating the AGN channel makes you look how many black holes you look at. But our initial reason was this model. So you cannot explain the stability and range and viscous timescales needed with this model. So you need unrealistic amount of supernovae happening at the same time to maintain this disk. And maybe there is some initial starburst epoch, but it's not sustainable. So, and if you have a large starburst epoch with heavier mass function, because like a lot of gas, then you expect to have a lot of black holes. So, and like I said before, it's either from the nuclear cluster that we know there's some population of black holes, or in situ, you do expect many black holes near centers of galaxies, and especially in disks.
Would the supernovas expel the black holes from the?
If the supernovas expel the black holes?
Yeah.
So, can you?
I mean, there's surely only supernova kicks that'll. I mean,
How strong are the kicks? I didn't consider.
I mean, there's a lot of energy imparted by supernovas.
But it's kind of like it's not symmetrical, but it kind of is. Like it's random, right? So it's not necessarily, yeah.
Even if you have a very strong kick of like 1% of C, for example, instead of light, anything within 10 to the 4 RG is going to be fine, because that's the velocities you have here on the central black hole. These are like relatively compact in galactic standards.
Yeah, but 1% of C is realistic for supernova kicks? No, right? So I didn't even. Yeah. So just like the kicks from the mergers, like the kicks from the mergers go to like thousands of kilometers per second, and they stay in the disk. So I think I'm not sure how strongly a kick from supernova is, but I'm not sure it can be that. Yeah.
General figure I see is 200 to 400 kilometers per second.
Yeah. Okay. So it's not an issue, even. You know. What?
The black hole kicks are much weaker
The neutron stars?
than neutron.
Mergers?
No, so the supernova kicks.
Oh, okay.
But on the neutron stars are generally what?
And how big are the neutron stars?
We don't know. There's no observational constraints, but we'd expect it to be much more.
Okay, yeah, okay. a collaborative answer. Yeah.
There are some there are some observational constraints on black hole kicks, and unfortunately they are somewhat puzzling, because on the one hand we know of some black holes which we strongly believe have almost no kicks, so almost complete fallback, and then there are other black holes where indirect observations, for example, looking at the typical scale height of black hole low mass exterior binaries versus typical scale height of neutron star low mass exterior binaries, actually suggests that the kicks may be somewhat similar in some of those cases, because the scale heights are comparable, surprisingly. There's probably an observational bias there, but yeah. So in general, I agree with your assessment that the kicks of black holes should be just from the notion of the fact that you probably expect to have
Maintain more mass.
momentum conservation, right? So that's what gives you the kick, right? And so even if you have a similar amount of ejected material with a similar velocity and similar degree of symmetry, you have more mass left behind in the black hole, so more inertia, meaning that the kick should reduce proportionally. Yeah.
I think it's safe to say that should we expect the black holes to remain in the disk? Maybe if not, they will be realigned after a short time. So hopefully we'll go with that. Any other questions? Some minutes.
So, I guess I'm missing maybe the big picture takeaway here. So, I'm a gravitational wave observer. That's all I know.
Okay.
What features am I looking for in my black hole distributions that's going to be the distinguishing factor between this and any other AGN channel or anything else?
What do you mean, any other AGN channel?
Well, as opposed to specifically with migration traps or anything. Or are you saying that's
Yeah, so I think the main question here is like the triangulation. So I know we in this run we,
not going to do it? Can't get you down to one galaxy.
no, well, not to one galaxy, but there's like statistical analysis like of over-representation of AGN, right? In the
Distribution, so I mean,
so for not necessarily like so I'm not sure of other literature, but if they can explain these 80 plus 60 solar mass black hole mergers in a robust statistical way, not fine-tuned system. So I'm saying you can really very easily get to these masses. Even if you forget about the fact that the black holes in the previous paper, we showed that they grow, and at some regions they grow to like you get a distribution of black holes that and non-negligible, like few percent, grow to like hundreds solar masses as well. So you have the gas and the hierarchical mergers, and just general robust statistics that say that you can grow to these masses. And I'm not sure there are systems that show it like in the same strength. So I don't know. But yeah, we would have triangulation, I think, is a really strong point here. Not specifically a single galaxy, yeah, but, and I think also AGN channel agrees with the spin distribution current generally, but yeah. Yeah, but yeah, I think maybe we'll think about how like observable.
Maybe eventually we'll do it. We'll work on that with electrical algorithms. No, to take some model simulations, couple that with like AGN prescriptions for torques. The location traps will give you locations where black holes will live long enough to interact and do things. I think we need to do embody simulations also with some prescriptions for spins to see how many generations they emerge, you know, what will be the mass ratio of the mergers. And I think this still needs to be done.
I think also long enough statistics, if the rates are high enough for hierarchical mergers, then like in a few like in 50 years we'll be able to say if we can point to AGN statistically, right? So yeah.
I mean, we could probably, with enough statistics, distinguish hierarchical mergers in the sense of 2G plus 2G from 1G plus 2G.
Okay, yeah. So with the n-body simulation and like some like more robust dynamics, then you can get like actual rates and see, you can compare the rates.
Yeah, I think even like the branching ratios between like 2G and 2G and like 1G and G.
Yeah.
But the problem is with rates, it gives you like the lower limit, right? Usually, or like or some top limit. Because if you have two systems that can gain similar results, you cannot distinguish between them. But okay, but so I'm not sure what will distinguish the AGN channel completely, but right now I think the ones that like contains almost all the other systems in the channels, because you have triple systems here. You have like, so I think it contains many of the answers that people try to answer separately. I think the AGN channel it's a good cooking pot for dynamics, and it contains many of the possible scenarios. Yeah.
Just want to like maybe a final comment on that is that there was a paper last year about that statistics. You just pretend, let's say most of the mergers are from AGNs. They actually found that they tend to be that of the luminous time, so it should be like of low luminosity, which is actually also refined for models without even trying to explain that.
Yes. So in the paper.
Sorry, what luminosity?
So
You have luminosity for the AGN.
Oh, okay.
So and they argue that most of the mergers will happen in low luminosity AGNs.
I see.
If this is the luminous channel.
So currently, statistically, AGN approximately above 10 to the 8 solar masses with 0.1 accretion rates. You shouldn't see mergers from them. Like observationally, you don't see. So, and it really fits this plot here, like so really nicely.
So Paul, just to comment on this, right? So the localization is not great, but the very bright AGNs are so rare that you can actually ask the question whether they are significantly overrepresented among the error boxes of observed systems, or they are no more overrepresented than you would expect from random placement. And the answer is they're no more overrepresented than you would expect from random placement for the very bright ones, which are rare, and so you can look at those individually. So you don't have an overestimate of overcount of them, and so that suggests that that probably at least there is not a very high fraction of observed LIGO mergers that are coming from AGNs with luminosities matching the very high, 10 to the 8 plus solar mass black holes.
And this considers like the whole areas of the big bananas, this paper. So yeah, so it's a robust result. Yeah.
I think beside a few minutes late, so we'll have maybe time for one last question/comment.
So, kind of related to what Paul was asking, so I also my previous question. So the type 2 migration traps in computing seem to be correlated with these opacity peaks.
And yeah, so the anti-traps are usually, yeah, there is a correlation.
So if that is true, and if that is either opacity peak, I'm not sure.
So not the type 2, not necessarily, because the increase, so this is even without table opacity, if you go in with radius, you need to increase the mass to open a gap. So that's a general feature, but the opacities make it like really in some regions like really strong cutoff.
Your contours looks like it was strongly
Yeah.
influenced by this.
So I think what happened is that the type 2 is a strong function of the scale height. It's like very large power law, and the extent of the skeleton disk, it's also correlates with the opacity properties because it depends on the south spin.
So the point I was trying to make was if that is iron opacity, I'm not sure actually, it could be helium, but if that is iron opacity, there is a metallicity dependence. Like if you use a more pristine gas which has less iron.
So we use here solar mass metallicity approximately. Yeah.
What I'm saying is if you use a low metallicity gas, that migration trap might not be there.
Yes.
It's completely erased.
Definitely.
In some cases, which means there could be a metallicity dependence in the amount of iron you have.
In fact, so a very good triangulation of Lisa statistics will give us like a metallicity limit, I guess. So if you see high mass black holes, but not as high as we expect, then you say, okay, so maybe the AGNs are less metallistic than with like have small metallicity, and we actually give a chemical limitation to AGN, which is really nice because that like it's we don't have
Even without triangulation, if you just take the
mass function.
Redshift distribution of the black holes, there could be the redshift dependence because the metallicity changes. Like I don't know, like if from population analysis.
But this also has bias with the mass function, right? Because the mass function also changes with redshift, so it's like so you cannot. You cannot necessarily distinguish.
Well, not necessarily, but there's a possible. I don't know. I'm just.
Yeah. I see what you're saying. I really like this direction. Maybe we can discuss it further.
So mass function just integrate over that, have like some cosmic evolution from the AGN channel, which would be nice to show.
So yeah, so this is another prediction Lisa can give us. Yeah, it's nice.